Most current machine vision systems separate sensing, memory storage, and processing. Photosensors capture, then data gets moved, converted, computed, then stored. That's slow, wasteful, and bulky. Biological vision, by contrast, senses and processes in one flow. The retina, synapses, nerves, brain codes, etc. If we can build hardware that more closely imitates that, integrating sensing, memory, and processing, we gain speed, energy efficiency, and compactness. That's where optical synapses come in, devices whose behavior, conductance, resistance, synaptic weight, can be modulated by light. Existing devices often need combined optical and electrical control, or use exotic, delicate materials, or lack full synaptic behaviors. They may work for excitatory or inhibitory responses, but not both, or fail when scaled or bent, or are too slow. The device in question uses a flexible silicon base with an MnOx PT stack.A. MnOx, a manganese oxide, is abundant and offers multiple oxidation states, NAND, MnN, which provide tunable vacancy densities crucial for modulating synaptic weights under light. The device is fully optical. Different wavelengths produce different responses. Under 465 nm blue light, it shows an excitatory response. Weight goes up. Under 785 nm near infrared light, it shows an inhibitory response. Weight goes down. And 532 nm. This device isn't just on-off. It shows a rich suite of behaviors: short-term plasticity, STP, and long-term plasticity, LTP, where brief light pulses versus repeated or longer stimuli cause different retention times of synaptic strength, paired pulse facilitation, PPF, and paired pulse depression, PPD, where responses to two pulses in sequence change depending on timing and intensity. The device remains functional when bent to a radius of 1.5 cm, making it suitable for wearables. One cell performs triple duty: sensing, memorization, and processing. When exposed to optical patterns, like handwritten digits under 465 nm, it can detect and recognize data in situ without transferring it to external memory, drastically reducing latency and energy consumption. It also functions as a non-volatile, reconfigurable logic gate using 465 nm and 532 nm as logic inputs and 785 nm as a configuration input, implementing and/or NAND and NOR operations by adjusting illumination and reading resistance states. Associative learning is demonstrated by pairing certain light input so future responses anticipate familiar stimuli. This behavior arises from MnOx, multiple oxidation states, and vacancy densities that shift under photon absorption. Light of specific wavelengths generates carriers, induces redox reactions, or alters trap states. The MnOx PT stack is tuned so optical absorption and trap densities align with those wavelengths, and temporal modulation, pulse duration, interval, and intensity transitions the system from SIT to LTP. The device's wafer scale flexibility suggests scalable manufacturability. Full optical control eliminates extra electrical components, reducing wiring, losses, and complexity, while bidirectional synaptic behavior enables richer computational flexibility. Integrating sensing, memory, and processing in one cell minimizes energy, latency, and circuit overhead, paving the way for wearables, bionic vision, and image sensors that compute where they sense. Logic and associative learning move these devices beyond simple memory toward adaptive behavior. However, challenges remain: device variability under different illumination or mechanical stress, long-term stability under ambient conditions, and optimization of MnOx film quality and spectral response control. Speed limits and precise recovery time control also need refinement, as does large-scale integration with existing systems. Still, This optical synapse device marks a significant leap toward neuromorphic vision hardware that unites sensing, memory, learning, and logic entirely under light. Real-time image detection, energy efficiency, and flexible form factor converge to promise wearable, bio-inspired vision systems that compute where they perceive. If engineers, materials scientists, and algorithm designers work together, such hardware could erase the boundary between sensor and processor, bringing artificial vision closer than ever to biological intelligence. If you enjoyed exploring this frontier where machines see and think simultaneously, like, subscribe, and ring the bell. Next time, we'll dive deeper into the physics of MnOx and its photodynamics and sketch how to build your own optosynaptic array. Stay curious.